Hey everybody, this is Dr. A, and in this example video, we are exploring more of material properties that kind of come from mechanics of materials and material science knowledge. So in this example, we are given this beam here. We have this beam, this horizontal beam that's being supported by an axially loaded support rod AB. So you have this kind of very simple pin connection between the beam at point A and then some kind of external support at point B. So both of these are like little pins. And then the beam itself is also being supported at a point C by an external hinge, okay? And so what we're being told to determine is the magnitude of the applied force P that causes this support rod AB to elongate by 0.0025 inches, okay? Now, we're also told that the support rod, which again is AB, has a 1/8 inch diameter and is made of A36 steel, okay? So this is all given information. Just to be a little bit more clear, we want to point out that this is the support rod, okay? Support rod. Now, what's a little challenging about this particular example is in order to kind of solve for what we need, we're going to have to apply some knowledge from statics. So, this is going to be statics kind of blended in with mechanics of materials and material properties, all right? So let's see how we're going to tackle this. So you want to maybe pause the video, write this down. Again, you want to, I've said this in all my videos, you want to write this stuff down. You're not really going to learn it by watching and listening. Pull out a notebook, pull out some paper, and do the calculations along with me to best understand. So we have the given information. We're going to go to solution now, okay? So the first thing that I would do to solve this problem is recognize that the thing we're really interested in is this rod. I mean, we have this kind of, simple enough system with a beam and, we have these dimension lines, but what we're really interested in is this support rod and how that's affecting the entire picture of the problem, okay? So here's what I would do. I would draw a free body diagram of the beam itself, okay? So let's do that. We're going to go back to our knowledge of statics, and we're going to draw a free body diagram of this beam. So, of course, we have the load P here, and then 3 feet away from the load P, we're going to have an axial vertical force that's developed in the rod. We can call this F sub AB. This is the force in the support rod FAB. And then all the way to the right, at the hinge at C, we're going to have a CY and a CX, okay? And then, of course, that is 7 feet away from the support rod. So if you remember from statics and physics, a free body diagram of a system is a simple diagram, usually with like stick figures, that shows all of your known and unknown forces, moments, and dimension lines. Well, also, if you remember from statics, whenever you have a simple rod or linkage, you just have an axial force develop in the direction of that rod. That's why FAB in this free body diagram is shown as vertical, and that's all you have there. It's like a simple rod or pin connected linkage, and then over at C is an external pin support, so that's why you have 2 external forces develop. And although we don't know the magnitude of P, that's what we're finding. P represents an applied force, so that shows up on our free body diagram, and also on your free body diagram you have the dimension lines. So again, free body diagrams show all of your known and unknown forces as well as dimension lines and any angles you may have. So that's a 3-foot dimension line. Forgot my little foot mark right there. So again, we're really interested in what's going on with the support rod. So how about this? How about from statics, we're going to say sum of the moments about point C equals 0. And we typically call things going counterclockwise positive. And when we sum moments about point C, CX and CY are not going to show up in this equation, but FAB and P will show up in this equation. So let's write this moment equilibrium equation. We're going to have P times 10 feet because we have this force P that has a moment arm of 10 feet away from point C. And then we're going to have minus FAB times 7 feet, and then all that is just going to say equals 0, all right? So this first term, P times 10 feet, is positive because P times 10 feet is causing a counterclockwise tendency of rotation, and we said counterclockwise is positive, and then FAB is causing a clockwise tendency of rotation about point C, and clockwise is going to be negative. And remember, we are assuming the direction of FAB is pointing up. Technically, FAB is an unknown force. So whenever you have an unknown force in a free body diagram, you assume a direction. You draw your free body diagram, assume a direction, perform your equilibrium calculations, and if something comes out numerically negative at the end of it all, your assumed direction is the opposite of what you assumed. So again, I'm just kind of splicing in a little bit of statics verbiage for our review. So again, we're interested in FAB, and we can solve for FAB as equaling P times 10 feet over 7 feet, okay? Again, all I did was I solved for FAB, and, you can kind of collapse this down as a decimal or a fraction, however you want to collect it, but it's just 10 over 7 times P, okay? Or, again, you could write that as maybe 1.429 times P. All right. So what we have here is we have FAB in terms of P. Okay. So the force developed in that rod AB is going to be 1.429 times P, which P is what we ultimately want to solve for later. So that's kind of the statics piece of this. Now let's look at the material properties and mechanics of materials piece of this. So we are told that this rod is going to elongate or stretch by 0.0025 inches. We know its initial diameter is 1/8 of an inch, and we know what it's made of. It's A36 steel. So let's go ahead and collect that information for our usage. So delta L is 0.0025 inches. Okay, that's the elongation of the rod. A36 steel, if you look up the material property for A36 steel, that has a modulus of elasticity of 29,000 KSI, or in other words, kips per square inch, okay? Now, the cross-section area, what's the cross-section area? Is it 1/8 of an inch? No, it's pi d squared over 4, where the diameter is 1/8 of an inch. So we're going to say pi times 1/8 of an inch squared over 4, and we can calculate that cross-section area as the following. I'm punching this in my calculator. I am using a TI-36X Pro calculator. I absolutely love that calculator. So I get a cross-section area of 0.01227 square inches. Write those units down, people. Write those units down. I'm going to go ahead and just double check that because I punched that in my calculator real fast. So yep, that is what I'm getting for that cross-section area. So crank this through in your calculator along with me. So here are all of our numerical values. Now, how are these related? So here's how we can relate them. For linear elastic behavior, which we're going to assume this rod is behaving linear elastically. That's a pretty okay assumption unless you're explicitly told or you have some information that tells you that it's not behaving linear elastically. So for linear elastic behavior, we can use Hooke's law. And Hooke's law allows us to relate average normal stress and strain. So we can say stress equals modulus of elasticity times strain, okay? And so how do we piece all of this together? Well, remember, stress, average normal stress, is going to be force divided by area. And for our rod, that support rod, what is that force? Well, that force is FAB. That's the force in the rod. And then we have the area of the rod as well that we just calculated here. We'll substitute that value in just a second. And then what about strain? Remember, strain is a change in length over the original length. And so that's going to be this 0.0025 inches divided by the original length of the rod. So I should have given you all that in the given information. So let me go ahead and put that in here. I meant to put this in here as 2 feet. I'm not going to remake this whole video because I forgot that 2 feet at the beginning. So this 2 foot rod, that 2 feet should be given information. Sorry about that. So that's given information, okay? So we're going to say that's divided by 2 feet right here. Now be very careful. You need to use consistent units. So how about we say 0.0025 inches divided by 24 inches. So we can go ahead and start substituting values in and punching things through. So 0.0025 divided by 24. So I get a strain of 0.000104. And I get an average normal stress of 1.429 P divided by 0.01227 square inches. So check out what's happening with this stress value. I have a stress value in terms of P, okay? 0.01227. So I get a stress value of 116.5 times P. I have stress in terms of P. Now I can use Hooke's law and put all of this information together. Stress is going to be equal to 116.5 P equals modulus of elasticity is 29,000 KSI, and then strain is going to be equal to 0.000104. And so solving for P, what do we get? We're going to have 29,000 times 0.000104 divided by 116.5. So I get a value of P equaling 0.0259 kips. Okay, so that's going to be that's going to be 25.9 pounds. Okay, now how do these units work themselves out? Well, remember this 116.5 carries units of 1 over square inches, right? So let's make a note of this. This has units of 1 over inches squared. So if this has units of 1 over inches squared, we can see that the inches squared will cancel themselves out and you're left with kips and then converting that to pounds on the back end. So that concludes this example. Again, rewatch it, pause it, and figure out your way through if there were some parts that may have been a little fuzzy to you. Thanks for watching. Please hit like and subscribe.